Welcome listeners. So again we have gathered here to discuss on the second part on the discussion on crystallography, and I am Dr. Shandy Banerjee, a faculty member in the Department of Geology, Banaras Hindu University, Varanasi. So before we plunge into the next part, one of the things that is important that we have left in the first part is indexing of phase that I was discussing, that if you are looking at the crystal parameters or if you want to quantify a crystal phase, then you need to have certain parameters like we have discussed about Weiss parameter, based on the intercept of the phases with respect to the each and individual axis, and also you have you can say a modified version of Weiss parameter, that is your Miller indices, which are always represented under first brackets. And like I was saying, that if you are looking at a phase that is cutting the A axis only, it will give you an intercept obviously of 1 infinity, means 1a, infinity b and infinity c. So if I take the reciprocals, it will become 1 by 1, 1 by infinity and 1 by infinity for c as well. So finally the Miller indices for that particular phase would be 1 0 0, and that should be also kept in first brackets. But if a phase that is cutting all the three axes at unit distance, again like this phase that you can see here, that is 1 1 1, so this is the final Miller indices. So the Weiss parameter was definitely 1 unit distance of A axis, 1 unit distance of B axis and 1 unit distance of C axis. And again if I simply take the reciprocal, so it will come as 1 by 1, 1 by 1, 1 by 1, and finally the Miller indices would be also 1 1 1, that is kept in first bracket. And the another thing that is important is zone symbol, like we have seen zone or zone axis. So if there are a set of faces, for example, again if I take this model, then these faces are belonging to a particular zone. Why? Because these faces are intersecting at these edges, and these edges are parallel to an imaginary axis which is passing through this crystal. So you have an axis simply that is passing through my two fingers through which I am holding this crystal. So this C axis or this axis, this imaginary axis, will be the zone axis to this particular set of faces. So now if I want to find out the zone symbol of this zone axis, in that case, for example, if you are dealing with two faces having Miller indices 1 1 0 and 0 1 0, and they are, in case they are not even parallel to each other, in that case as well you can find out the zone symbol that will obviously govern these two particular faces. So what I will do, I will write the Miller indices twice for 1 1 0 like this, again 1 1 0 for this, and again also 0 1 0 twice like this, and then I will simply drop off the first two digits and the last two digits, and what I will go for a matrix multiplication, and for that you will get this you can say 1 into 0 minus 0 into 1 from this matrix multiplication like this, and again 0 into 0 minus 1 into 0, and again 1 into 1 minus 1 into 0. So the finally your zone symbol will become 0 0 1. But in case if it is you are dealing with a zone axis for which you are finding the zone symbol, in that case that has to be put in a third bracket, not in a first bracket. For Miller indices only you will be putting it under first bracket, but for zone axis you will be putting it under third bracket. Now coming into the second part mainly, which is obviously one of the most fascinating part of crystallography, that is the presence of crystal and crystal symmetry. But before that, there are a few laws that needs to be discussed a bit that have been proposed by Nicholas Steno. So the first one is the law of constancy of interfacial angles. We have discussed about interfacial angle, the angle between the two adjacent faces of a crystal. So the law of constancy of interfacial angle suggests that if it is measured at the same temperature of with respect to a particular mineral, now I am talking about, I am taking two crystal of a particular mineral, for example quartz, I have taken two crystal at the same temperature, then always the interfacial angle will be exactly same, be it a quartz crystal that has been taken from the northern part of India or a quartz crystal that is taken from the southern part, somewhere in the southern part of India. If they have been formed in the same temperature condition, the quartz crystals has to always, they has to be same in terms of the interfacial angle. Obviously again, not any angle between any two face, it has to be the interfacial angle between two adjacent face, regardless of the size and shape of the crystal. Why? Because obviously the individual crystal are governed by the internal atomic arrangement that is already present in that particular mineral. We will be discussing also about the internal atomic arrangement in a bit. Then you have the law of rational indices. The law of rational indices states that the indices of any crystal face are always rational numbers, and that is the concept you can see through which your Weiss parameter are getting converted into Miller indices and are determined by dividing the intercept of the plane and clearing out the fraction. So that is the same thing that we do to convert a Weiss parameter into Miller indices. So you can also have this 110, 011, 111, these are all Miller indices of a particular face. Then you also have the law of axial ratio. The law of axial ratio states that the ratio between the lengths of the axis, like we were mentioning 3 axes A, B, C. So the law of axial ratio states that the ratio between the lengths, now individual lengths of the axis of a crystal of a particular mineral is again constant. So if you take a crystal of, for example, olivine, that is also a mineral. So if you take a crystal of olivine from two different places as well, then also the axial ratio of your olivine will remain same. For example, again if I take the axial ratio of a cubic crystal, like for example I am taking a pyrite mineral which is giving you a cubic crystal or the appearance of a cube. So in that case you will always get an axial ratio of 1:1:1. Now the most important part, like I was mentioning, is the idea of symmetry in crystals. So we'll first start with something which doesn't look like a face. Later on we'll discuss about the different symmetry. So if I take these three patterns like this one, there are a set of there is a set of fat little commas that are placed in space like this, and anything, always remember, anything that is giving you some kind of a pattern or any object that is in a pattern are nothing, they are termed as motifs. They are nothing but motifs. So I can say that these individual commas are motifs that are arranged in a particular pattern and they are forming a chain. So you can see there are motifs that are arranged in this chain. Also there are motifs that are arranged in this particular chain. You have a motif that is in the second chain, you have a rectangle with a concave shape. Again it is getting rotated, that will come to that, whether rotation or some other things are involved in it. So you have these three chains in here. So now if I start explaining, or if I start looking at the symmetry that these individual chains or patterns, that what kind of symmetry the first chain is possessing, what kind of symmetry the second one is possessing, what kind of symmetry the third one is possessing, then I can also start with a stamp like operation. For example, you have prepared a rubber stamp with these two commas that are placed on the rubber stamp, and you are stamping this as we move from the left to the right. So you started with a rubber stamp operation and you are simply moving a particular distance, you are again stamping it over there, again you are moving a particular distance, you are again stamping over there. So in this chain can be simply generated by the stamp operation that you can see. Now if I want to identify that what is this operation of this, means what is the true, in true sense, this is nothing but this is translation. So you are stamping some motifs in space, again you are moving at some distance, again you are stamping in the motifs in space, again you are moving a distance, again you are stamping the motifs in space. Likewise, you are generating the complete chain. So here what we are doing, we are trying to generate this complete chain with the operation of translation. So that means it has a specific direction where you are moving and stamping it on and on to generate the rest of the chain. Also, it also have a specific magnitude, because each and every time it is being separated at equidistant from one another. So now if I mark it as, for example, this first one, this is second one, this is third one, fourth one, fifth and sixth one, then I can say that 1 and 3 and 5, they are equidistant from one another. Similarly, 2, 4 and 6, these commas are also equidistant from one another. So here I can simply take, or I can simply write that this is the amount of translation we are concerned about. So here I can say, or I can keep T, or I can simply denote the translation as T. Now again, if I look at the second chain now, then also you have this similar kind of operation can be applied to this chain as well. If I start with this as, if I take this one as, this is 1, this is 2, this is 3, this is 4, this is 5 and this is 6, then I can say that 1 and 3, they are equidistant from one another, 3 and 5, they are also equidistant from one another. Similarly, 2, 4 and 6, they are also equidistant from one another. So if I now take this distance between 1 and 3 or 3 and 5, or if I take 2 to 4 or 4 to 6, you will always get the same distance, that means same magnitude, and we are moving from left to right in a particular direction. So you also have a direction. That's why it is denoted as the translation represented as T with a vector sign on top of it. So that's why the first, you can say the first symmetry element that is present in any material that possesses some kind of symmetry, or to be specific in any crystal, is the presence of a translation. So translation is the first operation of symmetry that is present in any crystal. So now this first one, be it the second one, be it even the third one, you can see that each and every time your translation is involved from one motif to another motif, or you can also take combination of motifs. Here in the first one or second or third one, I can also take combination of motif 1 and 2, then 3 and 4, then 5 and 6, and again always if I take the midpoint of this stamp like operation, I will also get the same translation throughout the zone. So now if I also look at the other symmetry operations that we can see over here. So apart from this stamp operation, what else we can think of? So again, if I take this particular, the first chain, then I can also say that motif 1 is related to motif 2 with a rotational kind of a symmetry, that you can generate second motif from the first one, you can also generate the third one from the second one, you can also generate the fourth one from the third one, and so on and so forth. So if I take a point or an axis through which your axis of rotation is passing through, and if I rotate it 180 degree from 1, then I can generate 2. Again, if I take another axis that is placed within 2 and 3, I can again rotate, now in this case anti-clockwise, and I can get 3. Again, with the axis that is passing in between 3 and 4, I can again generate 4 from 3. So like this I can generate 1, 2, 3, 4, even though apart from translation no crystal is possible, but apart from translation as well you can have other symmetry element, like we are looking into this one as rotational symmetry. So the rotational symmetry can give you 2 from 1, 3 from 2, 4 from 3, like this, so on and so forth. Similarly, if I also place the rotation axis in the second chain now somewhere here in between the motifs like this, then I can again rotate 180° and I can generate the second one from the first one, I can generate the third one from the second one, similarly so on and so forth. I can generate the complete chain. Even if I take some axis with 180° outside the chain, I can rotate the complete chain and again I will get the same set of patterns. Similarly for the first one, the second one, or even the third one. So the third one also can be repeated or can be generated, the whole pattern can be generated by the application of the symmetry element of rotation. So you can see that these three chains, all three of them, they possess the first element of symmetry, that is translation. All three of them, they possess rotational symmetry as well about an axis, which is also represented as A with an angle, be it the angle be it 180°, it could be 90°, it could be 60°, we will talk about that. And also the third one here, it also possesses a rotational symmetry. Now apart from that, what else is possible? So now if I look specifically at the second chain, I can also think of some planes which are passing through the center of the individual motif. So if I am passing a plane which is, if I am thinking about a mirror plane that is passing through the motifs, individual motifs, then what happens is I can generate, or this part of the motif is exactly a mirror image of this part. Similarly, this part of the motif is exactly a mirror image of this one. Similarly, this part is exactly a mirror image of this one. But remember that as the motifs are placed with respect to a translation, if I think about a mirror plane, then they also need to be in the same direction with the same magnitude. They needs to be placed in an uniform manner. You can't have a mirror plane that is related with the other mirror plane with some other translation, or with some other, you can say some other angle, or some other angular or linear parameters. So if these are your mirror planes, they has to be placed at equidistance. Even if I think of a mirror plane which is occurring just outside the chain, I can again repeat the whole chain with the help of this mirror plane, which is also the operation here. The element of symmetry is your plane of mirror. Your operation or the symmetry operation that is occurring is your reflection. So you are reflecting individual motifs as well as you are reflecting the complete pattern to generate the rest of the pattern. That is also possible. Similarly, now if I think about a mirror plane for the first pattern, can I have one mirror plane? No, I can't have any mirror plane in this, because there is no reflection symmetry that we can observe here. But now coming into the third chain, for the third one, you can also think of mirror planes that are present here like this. Okay, but in that case, what will happen, that if I am placing a mirror plane here, then the next one with the operation of translation will be placed here. That is fine, no problem. But then you are actually moving away from the original translation. The original translation of this set of motif is like this. So this is the original translation of, for example, T, that is having a specific magnitude in a particular direction. But if I think about this mirror plane, then the next mirror plane that should be associated with this particular set of mirror plane, they will get generated somewhere here. The next one will be generated here, then the fourth one will be generated here. So here we are compromising the basic idea of translation, because here you are not maintaining the same translation throughout this chain. Along this direction, a new chain is getting created if I consider this mirror plane as a symmetry element, or if I consider the reflection operation in this direction, then it will not give you this chain, it will give you a different chain. So that's why, though translation, rotation, these two symmetry operations are applicable for all these three patterns, it is not applicable to the third, but the operation of reflection, that is governed by the presence of the symmetry element, that is mirror plane, is only possible for the second one and not applicable for the first one and the third one, though overall individual motif they look exactly same as that of the second chain. Still, though there is similarity between the means you can say the overall geometry of the motif between second chain and third chain, but the problem is that if I consider the individual mirror plane in a motif in the third chain, it will generate the next mirror plane as well as the next motif in a different direction than what it should be in the same direction of the translation where about which your original chain has been placed. So, if I now think about and if I want to simply define that obviously an operation acts on a pattern as well as on space and not on a single motif. This statement is extremely important, that whenever we are talking about a symmetry operation acts on a pattern as well as on space, not on a single motif. So, if it is applicable to a single motif, it has to be applicable to all of space. It is not like that your individual motifs are getting only, or your symmetry operation is getting applied only to a single motif. It has to be applicable across or along the complete chain. So, now if I take another example in a simpler way to judge that whether this statement is correct or not, then I can simply take a star like structure or simply the structure of a starfish. So, for this star you can have mirror planes or reflection plane like this. If I have a mirror plane like this, then obviously the two parts will get reflected on one another. Again, I can take this as a mirror plane, this one as a mirror plane, this one as a mirror plane, as well as this one. So, you can simply have 5 mirror planes which in its own way they will reflect the other half of the star or the starfish onto the other half. So, the operation or you can say the implication of the presence of a symmetry operation is that a symmetry operation will map a pattern in congruence with itself. So, if I say that reflection is a symmetry operation with the help of a symmetry element, that is mirror plane, it will map one half of the star on the other half of the star exactly into congruence into itself. So, you can have 5 mirror planes in this case. If I look into this, then if I think about a different rectangle or rectangular box like this, then individually if I say you can also have mirror planes like this too. You can't have diagonal mirror planes because it is not a square. In case of square you can also think of diagonal mirror planes, but if it is a rectangle you can only think of these two mirror planes. Now, there are 5 mirror planes which are strictly applicable to this particular star, as well as there are 2 mirror planes which are strictly applicable to this particular rectangle. Then if I now combine, or if I simply take out this star and put it on this rectangular box, so what will happen? If I combine this, then now you can see that out of this 5 plus 2 means there could be 7 mirror planes, but now you are considering the star and the rectangular box in totality. So, in space, how many of this mirror plane are now applicable to this final version of this combined star and rectangular? You can say only one, because here you can't have this mirror plane which is applicable to the rectangle. Why? Because it won't reflect the star back to congruence with itself. Similar problem will arise with the rest of the 4 planes that were applicable in case when you were only dealing with the star. So, the rest of the mirror planes that were present like this for the star, like this, they are no longer again applicable to the rectangle. So, the only one unique plane which is applicable to both these structures, the star as well as the rectangle, is nothing but your this vertical mirror plane which is applicable to the all of space. So, again to be specific, an symmetry operation acts on a pattern as well as on the space, not on a single motif. If it is applicable to a single motif, it has to be applicable to all of space. It is not like that a symmetry operation can be present only if I consider a motif. You have to always consider the whole of space. So, if I say now with the example of this again particular crystal, then if I say that if I am having a mirror plane going like this, or I can use this contact goniometer, if I say that I am keeping this mirror plane like this, then this mirror plane will reflect the left side of the crystal onto the right side of the crystal, and you can see this mirror plane or this plane will act as a reflection plane on this particular crystal. But now so this part is applicable to this, but it is also applicable, the same mirror plane, if I now rotate, I am not changing the position of the mirror plane, I am just changing the position of the crystal, or I am rotating the crystal. You can see on the top as well, it is giving you a mirror image with the left hand side of the crystal to the right hand side. Similarly, at the bottom of the crystal as well, you are getting mirror image on the left side to the right side of the crystal. So, you can see this mirror plane is not only acting to this particular face, it is acting on the top of the crystal as well, it is acting on the bottom of the crystal as well. So, if I am talking about any symmetry operation, then it is not only applicable to a particular plane, it has to be applicable to all the planes that are present in that crystal. Now, again to summarize the symmetry elements. So, in 2 dimension we have symmetry elements starting with translation, which is denoted as T with a vector on the top. Then you have the operation of reflection, the symmetry element is your mirror plane. Then also you have the operation of rotation, the symmetry element is an axis of rotation, because any rotation, for any rotation you need certain axis. So, that axis has to be the symmetry element, and the rotation, be it 180 degree, 90 degree, 60 degree, whatever it is your axis or the operation of rotation. Whereas, in 3 dimension you have an additional symmetry element, that is your center of symmetry, about which your inversion of faces occurs. For example, again if I take this, now a different crystal I am taking a rhombic kind of faces, you can see. So, if I say that this crystal possesses a center, then this face will have an inverted kind of a face on the other side of the crystal. So, if I compare this, you can also rotate it, you will get the same face. If I simply invert the crystal, you will get the same face. So, this face you can see is sloping towards you, and if I again rotate it, again you are getting a face which is also sloping towards you. So, and this inversion is actually taking place about a center that is present at you can say the imaginary center of this wooden crystal. So, you can have, I can also draw a simple diagram depicting that how it might look, that if this is your z axis, this is minus z or bar z, this is your x, this is bar x, this is your y, this is your bar y. So, if you are having a motif here looking like this, then you will also have a motif sitting right over here. About this thing will be inverted about this center like this. So, it is an inversion that is taking place here. So, obviously, in case of a 3-dimensional reference frame, when we are talking about 3-dimensional symmetry, you have translation, but remember translation we can't directly see, because these are symmetry elements which are of, you can say, atomic scale or molecular scale, because your individual atoms, how they are placed with one another, they will give you an idea of the translation. So, you can't directly see it through your naked eye, but the presence of mirror plane giving you reflection, you can identify that. The presence of a rotational axis, you can think of axis, and you can also think of rotation, you can identify that, as well as like I have just shown here, you can think of inversion about a center. So, like this, these are the symmetry elements that we will be dealing through the rest of our lecture, as well as in case of one dimension, what is happening, you only are left with translation and the presence of reflection operation, that is mirror plane. So, in one dimension you have only two symmetry elements, in two dimension you have three symmetry elements, in three dimension you have four symmetry elements: translation, reflection, rotation and center of symmetry. So, like this one, again in the simple diagram, this shows this two is the, you can say this one possess a center of symmetry which is sitting somewhere, you can say somewhere here, and this one, this particular crystal does not possess any symmetry, because you will not find an inverted face of this on the other side of crystal, but you will find an inverted face on the other side of crystal in the first case. So, here you are getting a center of symmetry that is sitting right at the center of the crystal here, but in this case you are not getting any kind of center of symmetry. So, we will also continue our discussion on symmetry theory in the third part of this lecture. So, here I would like to conclude with this idea of symmetry, that anything that we see around us possess some kind of symmetry, be it only translation, be it a combination of translation or reflection, be it a set of translation, reflection as well as rotation. You can again think of this crystal before I conclude. You can rotate this crystal, you can generate same faces again and again. You can also, like I have shown, you can put a mirror plane, you can reflect one half of the crystal onto the another half. You can also do that with this crystal. Also, if I think of an imaginary center that is present at the center of this crystal, you will get a face which is just an inversion of this. So, if I rotate it, you will get same face after an inversion to the first one. So, this one will give you a same face even after rotation, like this. So, you are again getting the same face even you have rotated or you have inverted the crystal. That is why the operation is referred to as inversion operation, but the element is referred to as center of symmetry. Okay. So, these are the four symmetry elements that we will be dealing with for the rest of the discussion on crystallography. Thank you.